session, we'll be going through the Combined Science Chemistry Paper 1 from the exam board Pearson's Edexcel. Please make sure that you do have a calculator to hand. Salts of metal can be prepared by reacting the metal with an acid to produce salt and hydrogen gas. Describe the test to show that hydrogen gas is produced. So the test is that you put a lid splint towards the gas, and if the gas makes a squeaky pop, that proves it's hydrogen gas. In the next question, we are told that nickel is a metal. Explain how the structure of nickel atom Ni changes when it forms a nickel ion. So for the nickel atom to form a positive ion, it must lose electrons, and because it forms a 2+ ion, that means it's lost 2 electrons. Now for part B, a nickel sulfate solution is made by dissolving 23.5 grams of nickel sulfate to make 250 centimeters cubed of solution. Calculate the concentration of the solution in grams per decimeter cubed. So what we would do is, first of all, because we've got 250 centimeters cubed of solution and we're wanting grams in a decimeter, we need to know how much more 1 decimeter is compared to 250 centimeters cubed. So if we do 1000, which is a decimeter cubed, so 1000 centimeters cubed is a decimeter cubed, and we divide it by 250, which is what we had, that tells us that 1 decimeter cubed is 4 times as much as 250 centimeters cubed. So if we're going to have 4 times as much water, we are going to need 4 times as much of our dissolved nickel sulfate. So we would do 23.5 times 4, and that would give us 94 grams per decimeters cubed. So that would be 94 there. In part C, we're told that excess solid nickel carbonate is added to dilute sulfuric acid in a beaker. Nickel sulfate is formed in solution. Describe how a sample of pure dry nickel sulfate can be obtained from the mixture of nickel sulfate solution and excess solid nickel carbonate in the beaker. Now that part's important because they've told us that we've got excess of our solid nickel carbonate. So the first thing that we have to do to get rid of the excess solid is we have to do filtration, so the solid and any extra solid nickel carbonate is removed from the solution. Then we would form crystallization on the solution by heating it up, allowing it to cool and the crystals to form. Now, in this question, we're told that most metals are extracted from their ores found on the Earth's crust. The method used to extract a metal from its ore is linked to the reactivity of the metal, and we're shown part of the reactivity series in Figure 1. So we're having the metals put in order from least reactive at the bottom to most reactive at the top. Then we're told that iron ore contains iron oxide. And when we're looking at this, we're given the equation. So iron is extracted from iron oxide by heating heating the oxide with carbon. So we end up with iron and carbon dioxide being produced. So it says in this reaction, we've got to choose from one of the answers. A, carbon is reduced. B, iron oxide is neutralized. C, iron oxide is reduced. Or D, iron is oxidized. Now, if we think about reduction, you've got to remember that the loss of oxygen is reduction. And that's the key to answering this question. So if we have a look, the correct answer is C, because the iron oxide is going from having oxygen to not having oxygen. So the iron is being reduced. The carbon is going from not having oxygen to having oxygen. So the carbon is being oxidized. So the formula of iron oxide is Fe2O3. Calculate the maximum mass of iron that can be determined from 240 tons of iron oxide, and we're given the relative atomic masses. So first of all, we would work out the molecular mass of our iron oxide, and that would be 2 times 56 for the iron plus 3 times 16 for our oxygen, and that gives us 160. Now, if we're looking at how much iron can be made from the iron oxide, we have 2 atoms of the iron in the iron oxide. So that means the 2 times 56 is telling us how much iron there is in the iron oxide, and that's 112. So what this means is, so because we're looking at tons here, if we talk about this in tons, if I've got 160 tons of iron oxide, I will have 112 tons of iron in there. But we're not trying to find out how much 160 tons would produce. We need to find out how much 240 tons would produce. So we need to work out how much bigger is 240 compared to 160. So what we can do is we could do 240 divided by 160, and that equals 1.5. So if I times 160 by 1.5, I would have my 240 tons to start with. Now, if I times that by 1.5, that means I would have 1.5 times the mass of the iron that I would get with 160. So now I can work that out, because I would do 1.5 times 112, and if I do that, that would tell me that I would have 168 tons of iron being produced. So my answer here would be 168 tons. Now in part B, we are told that aluminium cannot be extracted by heating its oxide with carbon. Aluminium has to be extracted from its oxide by electrolysis. Explain why. So this is because aluminium is more highly reactive than the carbon, so it cannot be extracted by carbon reduction. So for part C, it says predict the method that will have to be used to extract calcium from its ore. So this would be electrolysis. And electrolysis is where you use electricity to split up the ions in the compound. And part D says in recent years, researchers have been investigating alternative methods of extracting metals from soils. Researchers have found that growing certain plants in appropriate areas can result in the phytoextraction of copper. Describe how growing plants can result in the phytoextraction of copper. So basically, this process involves growing plants that will absorb the copper ions from the soil, which are then stored in the plant and can be extracted when the plants are burned during the harvest. So for question 3, part A, which of the following substances would be solid at 20 degrees Celsius and will melt when placed in a beaker of hot water at 80 degrees Celsius? So room temperature 20 degrees, so B and D will already be liquids at room temperature, so it can't be those two answers. Now, if we look at C, if you put it into a beaker of hot water at 80 degrees, will definitely melt because the melting point is 30 degrees, whereas A would not because its melting point is higher than 80 degrees. So the answer which is correct is C. Then in part B, a student sets up the apparatus as shown in figure 2 to obtain pure water from seawater by distillation. Explain how the water in seawater separates to produce the pure water in this apparatus. So, first of all, the water that is heated in the conical flask will evaporate to form water vapour. Then the water vapour will cool and condense to form pure water in the test tube at the end of the delivery tube. So for part 2, explain how the apparatus could be improved to increase the amount of pure water collected from the same volume of seawater. So here what we could do is we could put a beaker of iced water around the pure water that's condensing, and that means that the pure water vapor that's condensing will cool more quickly, condense more efficiently, and less of the vapor will be lost as gas to the atmosphere. For part C, a substance is heated at a constant temperature and its temperature is taken every minute. During the heating, the substance undergoes a change of state. The results are shown in figure 3. Explain the shape of the graph in terms of changes in movement and arrangement of particles as the substance is heated. So, first of all, if we look from A to B, we can say here that the particles are arranged as a solid, and as the solid is heated over time, the particles are gaining energy, so vibrating about their fixed position more rapidly. Then for part B to C, we can say the graph here is flat because the particles here are using all the energy that they are gaining to break their intermolecular forces. Then for part C to D, here the graph is starting to rise again, but here the particles are arranged as a liquid, so the particles can move past one another, but as they gain more energy, they are moving faster. So for question 4, molten zinc chloride is an electrolyte. Which row shows the products formed at the anode and the cathode when molten zinc chloride is electrolyzed? And that's important that it's molten zinc chloride. So we're going to have zinc ions and chloride ions. And the chloride ions will be attracted to the anode, and the zinc ions would be attracted to the cathode. So the correct answer would be C. For the next question, it says, which of the following is the reason why molten zinc chloride is an electrolyte? So we say it's an electrolyte because the ions are free to move. So the correct answer here would be D, because the ions are able to move. Then for part B, copper sulfate solution was electrolyzed by copper electrodes. Draw a label diagram showing the apparatus that is used to carry out the electrolysis in the laboratory. So first of all, we need to make sure that we have a power supply. The power supply then will be connected to our electrodes. We need to make sure that's connected to our electrodes. And then the electrodes will be in the copper sulfate solution. So we have to label the copper sulfate solution. We can label our cathode and our anode. And here we've got our power supply. Before the electrolysis, the masses of the electrodes were determined. After the electrolysis, the electrons were washed, dried, and their masses redetermined. figure 4 shows these masses and the resulting changes in the masses. So at the anode, we can see that we had a loss of 0.85 grams, and at the cathode, we had a gain of 0.85 grams. And we have to explain these results. So we can do this in two ways. We can do this in a wordy way, or we can do this as an equation. So we could say at the anode, the copper atoms become copper ions and they lose two electrons. Lose two electrons. And we could write that as an equation as a copper atom becoming a copper ion plus two electrons. And then at the cathode, we can say that the copper ions become copper atoms and gain two electrons. And we could write that as an equation as the Cu2 plus two electrons becoming the copper atom. Now for part C, when sodium sulfate solution is electrolyzed using inert electrodes, hydrogen is formed at the cathode. Write the half equation for the formation of hydrogen gas, which is H2, from hydrogen ions, which is H+. So we're being told that we're going to form hydrogen gas, which is H2, from hydrogen ions, which is H+. So when we look at that to start with, we can see that if we've got two hydrogens at the end, we need to have two hydrogens at the start. So we have our two H pluses, which are going to make H2 at the end. And if I've got two H pluses, I will need to add two electrons onto my two H pluses for it to form H2 at the end. And that's my half equation. Question 5. Covalent substances can be simple molecular, covalent, or giant covalent. Ammonia is a simple molecular covalent substance. Which is the most likely set of properties for ammonia? So if we're looking at simple covalent, they have low melting and boiling points. So it's going to be out of B and C. So for question 5, covalent substances can be simple molecular covalent or giant covalent. Ammonia is a simple molecular covalent substance, which is the most likely set of properties for ammonia. So if it's simple molecular, it's going to have a low melting and boiling point. So it's either going to be B or C as our answers. And if we move across and we look at the properties, covalent substances do not conduct electricity. So the correct answer here would be B. Then ammonia, NH3, is made by reacting nitrogen and hydrogen. Write a balanced equation for this reaction. So we know that ammonia, we've been told, is being produced. And if ammonia is being produced and we're starting off with nitrogen, nitrogen gas is N2 and hydrogen gas is H2. So now what we need to do is we need to balance our equation. So if we have two nitrogens on our reactant side, we need two nitrogens on our product side. But now we have six hydrogens on our product side, so we need six hydrogens on our reacting side. Then we're told that oxygen, O2, is also a simple molecular covalent substance. Draw a dot and cross diagram for the molecule of oxygen. So we've got to remember oxygen is in group 6. So it's going to have 6 electrons on the outer shell. So I'll put an O in the middle showing that it's oxygen. And because oxygen has 6 electrons on the outside, the oxygen is going to share 2 of its outer electrons in a double covalent bond. So we will have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And now we can see that for each oxygen atom, we have 8 electrons in the outer shell altogether, because we've got 4 in the middle and then 4 on the outside of each of them. In part C, we are shown figure 5, which shows the arrangement of carbon atoms in diamond, graphene, and a fullerene. So we're looking at allotropes of carbon. What we have to do is we've got to consider the 3 substances and we've got to explain in terms of their structures and bonding their relative melting points, their strengths and ability to conduct electricity. So when we're considering our answer, for each of the three different allotropes, we have to say how many covalent bonds they have. So diamond has 4 covalent bonds, whereas graphene and fullerene has 3 covalent bonds. Because the covalent bonds are strong for diamond and graphene, that means that the melting points are going to be high and they're strong structures. However, because the fullerene, when we're melting the fullerene, we're breaking the weak forces, intermolecular forces, between the molecules. The fullerene has the lowest melting point out of the three. Diamond will not conduct electricity because there are no delocalized electrons, because all the electrons are involved in the covalent bonds, whereas graphene and fullerene will conduct electricity because for every carbon atom there is one delocalized electron which is free to move, therefore will conduct electricity. Now for question 6, it says a student placed a piece of metal P in a test tube containing excess dilute sulfuric acid. The student repeated this with 3 other metals, Q, R and S. All the pieces of all 4 metals were the same size. The student recorded the observations until each metal had reacted with the acid for 2 minutes. The observations are shown in figure 6. Now, we've got to look at the observations and we've got to use the information to put the metals in order of reactivity, from least reactive to most reactive. So if we look at P, we've got bubbles are produced slowly and we've got some metal remaining. If we look at Q, we're told that bubbles are produced quickly, no metal remains. R, bubbles are produced slowly, no metal remains. S, bubbles are produced very quickly and no metals remain. So in terms of our slowest, we've got 2 that are slowly, but 1 where metal remains, so that's our slowest, so that would be P. Then our next slow reaction is R, and then if we look at our 2 quick reactions, we've got quick and very quick, so quick would be Q and very quick would be S. So in this question, we're told that we need to complete the diagram to show how the student could add to the apparatus to measure the volume of the gas produced in 2 minutes. So to collect the gas, we will need a delivery tube, which is connected to our gas syringe. So we would draw our gas syringe like this, and then we would draw the middle part of our gas syringe there. But the second thing is we need to make sure that we have a bung that is connected to the top of our test tube so no gases escape into the atmosphere. Then for the next part of the question, we have when iron reacts with copper sulfate solution, solid copper is formed, and we've got 2 equations A and B. It was found that when 10 grams of iron powder reacted with excess copper sulfate, the solution produced 11.34 grams of copper. Carry out a calculation to decide which equation A or B represents the reaction taking place. So the differences between these is the amount of moles that we're starting with in terms of our copper sulfate solution and our iron. So if we look at our first details that are given to us, we have iron powder, we have 10 grams. So if we remember our equation where the number of moles is mass divided by molecular mass, for iron, we can work out that if we have 10 grams and we divide it by the molecular mass, which is 56 grams, that gives us 0.179 moles. And then if we do the same with the amount of copper that we've used, so copper, we have 11.34 grams and we divide that by 63.5, which is the molecular mass, that also comes out at 0.179 moles. So we're looking at a ratio of 1 mole of iron reacting with 1 mole of copper. And the correct equation for that to happen is going to be equation A. So equation A is the correct equation because we have a 1-to-1 ratio. So in this question, acid solutions contain hydrogen ions. Aluminium reacts with dilute hydrochloric acid to form a solution containing aluminium ions Al3+. Complete the balanced ionic equation for the reaction. So if we've started with Al3+, and we know we're going to have hydrogen gas formed at the end, we know that the amount of hydrogen ions that we started with have to be a multiple of 2. Now, if we've got 3+, we want to have a number that 3 and 2 both go into, so that would be 6. So to make our 6+ aluminiums charged here, we would have to do 2 times Al3+, and to get 6+ on our reacting side for our hydrogens, we would have to have 6 H+ on our reacting side. Now, if we've got 6 H+ ions, we need to make 6 hydrogen atoms, so that would be 3 H2 molecules. And if we end up with 2 aluminium ions, we must start off with 2 aluminium atoms. Now, the hydrogen ion concentration in a solution is decreased by a factor of 10. So we've got a decrease by a factor of 10 of the H+ ions. State how the pH of the solution changes. So if we've got a decrease, that means that the actual pH is going to increase by 1. Now for part E, it says calculate the mass in grams of a hydrogen atom using the data below. So the relative atomic mass of hydrogen is 1, and the Avogadro's constant, that is the mass of 1 mole of atoms, is 6. So that's the number of atoms in 1 mole is 6.02 times 10 to the power of 23. So we know that if we've got 1 gram of hydrogen atoms, that is 1 mole, and 1 mole of atoms is 6.02 times 10 to the 23 atoms. So if we need to work out what the mass of 1 hydrogen atom is, we would take the mass of 1 mole of atoms, which is 1 gram. We would divide it by how many atoms there are in 1 mole, which is 6.02 times 10 to the power of 23, and that will tell us the mass of 1 hydrogen atom. And if you work that out, you get the mass as being 1.66 times 10 to the minus 24 grams. So that's the mass of 1 hydrogen atom.